All right, well, welcome everyone to BEAM, what you need to know about do-it-yourself carbon material modeling. This course is hosted by the Green Home Institute. The Green Home Institute is a nonprofit with a mission to empower people to make healthier and more sustainable choices in the renovation and construction of the places we live. Today, I will be your moderator. My name is Brett Little, and I am the program manager here. As always, our courses are approved for multiple continuing education units. Among many is our Certified Green Home Professional, and this one will be in the materials pedal, as well as AIA Health, Welfare, and Safety, which may make it applicable to your state-based design or contractor license. If you haven't become a member yet, we've only got a few of these corn-based mugs available, grown right here in the good old USA. And so we'll send that out to you, plus you get instant access to all of our webinars, certifications, discounts on air quality monitoring, and we are doing a book giveaway today. Chris, I don't know if you want to pop in real quick before I have you come back, but show everybody what they might win. Our members can access or receive a copy of Chris's latest book, Build Beyond Zero. All you have to do is be a member, so you can sign up right now and then stay for the entire session, and you might win a copy. So thanks, Chris. And then briefly before we get into it, I've got to say a huge thanks to our top tier sponsor, Indo. Can you imagine having storm windows on the inside? Well, it's real. And when it comes to existing homes, replacing windows is going to be a massive embodied carbon penalty. And so, and cost, right? We can't afford it these days with inflation. So why replace windows when you can repair, reputty, and then put storm windows either on the outside or these new types of windows, which can be do-it-yourself friendly, added right on the exterior or the interior of the house. And these are Indo inserts are made from acrylic panels edged with a soft patented silicone compression tube that presses into the interior windows frames to seal the drafts. And there's been studies to show whole home retrofits done with these. Retrofits is a strong word there, but updates can reduce air leakage by 10% potentially. This was a third-party study. So you can check them out over at indowindow.com. And then thanks to our second-tier sponsor, Niagara. As you can see, we need to start cutting our water usage. We're facing droughts and increase in water costs. I like to say water costs we're ahead of the inflation trend before inflation became cool. So water bills have been going up, and we can get them down to 0.8 gallons per flush on toilets easily with vacuum assist technology to help. And it works very well. I haven't seen any problems with it. Neither have our multifamily housing developers. Down to 0.8 gallons per flush. If you're too nervous to go that low, that's okay. They have 4 other lines, Liberty, Sabre, Shadow, and Baron, that have a little bit higher flow rates, but still WaterSense certified. Still going to get you down. Check it out at niagaracorp.com. Well, I am excited here to soon hand it off to our speaker. He's been with us, I believe this is the second time on the show, so it's exciting to have him back. Before I, hand it over, I'm just, we have an ongoing embodied carbon series that we've been doing, so you can check that out on our YouTube channel, and this will be added in addition to it. The reality is you've all been with us for so long, and you know that you can get net zero energy construction, right? Operational, right? This is easy. And now with the new incentives that are coming out, it's no excuse not to be net zero operational starting today, day one, and even on our renovations. You all know that. But the biggest problem is once we do that, our problem will be on the carbon will be on the material side. And so we've got to find a way to immediately start to move forward and do that. Our Green Star Home Certification Program, if you're following it and building new, you'll actually be required to model your embodied carbon and then reduce it as well. And so we're going to be using the BEAM tool as one of the pathways and one of the easier pathways, I believe, to do that. So that's why I'm super excited here to hand it off to Chris Magwood to take us through a higher level introduction to why this is important, how it can be done, and what you can do next. So Chris, welcome back. Please take it away.
Great. Thanks, Brett. Thanks for having me, and thanks everybody for showing up and spending a part of your day here with me and all the good folks at the Green Homes Institute. I'm just going to find my screen to share here. There we go. Okay, so like Brett said, I'm going to talk to you about the carbon footprint of the materials for new homes and for renovations, and look at some reduction strategies that home builders can take to make a pretty big dent in those what we call material carbon emissions, and take a look at the BEAM tool that we developed here at Builders for Climate Action to help people be able to do that. So just a quick introduction of myself. My name is Chris Magwood. I have kind of two hats these days. One is that I'm with Builders for Climate Action, which is a small organization based up here in Ontario, Canada, where we have been working on embodied carbon in materials for the last few years, including doing some fairly large studies that I'm going to show you. I have also recently joined the Rocky Mountain Institute, RMI, on their embodied carbon team, and starting to do more work on this, this topic in the US along with them. But my background is actually as a design builder. I have been designing and building for over 25 years now. This is a selection of the homes and commercial buildings that I have worked on in my career. And the work that I've been doing on embodied carbon kind of comes from my practice, which has been to really try to make our take on what makes a green home very metrics based. And so for a couple of decades now, we've been working with things like energy modeling and stuff like that to really have good metrics on the operational side of the building, also looking to use metrics for indoor environment quality and material toxicity and water and all of those things. And that interest in trying to figure out actual metrics for things that matter in buildings led me to try to figure out the carbon footprint of the materials in our projects, and the lack of great answers or helpful tools when we started doing that sort of led to the development of BEAM and, in fact, the whole Builders for Climate Action organization. So what I'm going to share with you, sort of, it comes from me as a researcher, but it comes from also a really firm grounding in practice as a design builder. So, everybody here knows that we have been working hard to address emissions in buildings from the operational side. And that, wherever you happen to look at this issue, if I'm looking at it in, Ontario, Canada, you find the same results all across North America and, in fact, around the world, that are basic business as usual, where we're using either fossil fuels directly or fossil fuel powered electricity, and very minimum standards for energy efficiency in those buildings. What all that has amounted to is a huge amount of emissions coming from the operation of our buildings. This case study of a two-story house in Toronto, Ontario, is 3.5 tons a year from a code minimum building in Toronto right now. And so if you sort of project that out over 20 years, you're looking at 70 tons of emissions, per typical new home. And, at that rate, we're not going to be able to address our climate issues. And so, all of us have been working hard to bring this down. We know that if we electrify buildings, if that electricity comes from renewable energy, and we increase the efficiency of the buildings, we can see, drastic improvements in the operational carbon footprint of our buildings. Getting down, well under 0.5 ton per year, even in a really cold climate like here in Ontario. And in fact, when you add renewables to that, actually being able to zero that out. And like Brett said, we have a pretty good sense in our practices of how to do this. But the sort of part of the equation that's been missing when we look at the carbon footprint of our homes is, what are the emissions that come from creating the materials in the first place? So in other words, that line that we've been using that, used to start at 0 on operation, depending on the efficiency of the energy source, that's great. But there's actually this sort of burst of emissions that happens up front when all the materials for that building or even that retrofit were first made. And if we don't know that, if that remains a big giant question mark, then we don't actually know what the carbon footprint of a new building or a retrofit will be, because we're missing this big chunk that happens up front. And so that chunk, that material emissions plus the operating emissions, is what gives us what we've started calling here at Builders for Climate Action the carbon use intensity. It's basically, what is the carbon footprint of the building over a certain period of time? Well, that's going to be, the emissions from the materials plus the emissions from operating put together give you that carbon use intensity. And the way that we can estimate that is by using reports called EPDs, Environmental Product Declarations. And we use the results from EPDs in our BEAM tool, as do other places that are starting to measure this with tools. And we get material carbon emissions, and it's typically measured in kilograms of CO2e, which is carbon dioxide equivalent. So it's counting all the greenhouse gases that get emitted in the supply chain of making a material. So, if there's methane or other gases besides CO2 emitted, it's all kind of put in the same common denominator of carbon dioxide. So CO2e is kind of the shorthand for capturing all the emissions that happen from all the different gases. And an environmental product declaration is a report that summarizes a life cycle assessment of a material, and it sort of follows an ISO standard so that it makes the life cycle of a product sort of comparable between products in the same category. EPDs don't work to kind of compare products across categories. So, there's not a lot to be gained from, say, comparing the carbon footprint of concrete with the carbon footprint of glass, because you use those things for different reasons. So there are what are called product category rules. And the idea is that emissions in the same product category are measured in the same way. And then that makes products with an EPD kind of comparable within their own category. And there are a whole bunch of organizations that verify EPDs. So, the great thing about relying on EPD data for a study or for measuring the carbon footprint of your own project is that the results are verified by well-known programs across North America, like ASTM and NSF and all the other ones that you can see there, UL. And that means that we have a pretty good degree of certainty that what we're looking at in an EPD is true and therefore comparable across the product types. And so what you get from an EPD, EPDs are interesting because they give you this information, but what you get is sort of a very raw version of the information. So, for example, if you look at EPDs for timber, concrete, and steel, you'll get results like you see on the screen here. So it'll say timber, and this is for, in this case, all of North America. It's an average is 42.56 kilograms of CO2e per cubic meter of wood, of softwood lumber. And then for concrete, you'll see that it's there's an average in the US of 304.53 kilograms of CO2e per cubic meter of concrete, and that steel is shown as 1.16 tons of CO2 per ton of steel. So you have that raw information, and that's maybe great, maybe not great, because just looking at that, we have no way as builders of knowing whether we should, say, be using timber for a post in the basement of a home, or concrete or steel, because there's no kind of common denominator here to to be able to make that comparison. So the EPDs are great in that we get this sort of source data, but it's, it takes another whole layer of calculations if, as a builder, you want to figure out, what this means for your project. And so that's why we ended up designing Beam. We designed it first as an in-house tool to be able to do these background calculations, and then in May of this year released it publicly. And so what Beam does is it takes a material quantity that we get from the user who inputs actual dimensions of the building. We take those dimensions and turn them into material quantities, and then we multiply that by those emissions factors that we get from EPDs, and that allows us to give an answer on the material emissions for a particular type of a particular amount of material that you would be putting in your building. And at that point, you can start to make informed decisions. So if you think about the timber, concrete, and steel numbers I just gave you, those are for amounts of material, but until you know how much of that material is going to be in your building, you don't know what the answer is going to be. So Beam kind of does what you see on the screen here. It takes the EPD data for emissions per a quantity of material. It figures out how much material is, say, in your 6x6 post, and does the background math to say that, one 6x6 by 8 foot tall post in your basement has 4 kilograms of emissions associated with it. If it was a 6-inch in diameter concrete post, it would have 12 kilograms of emissions. And if it's a 3.5-inch diameter hollow steel post, it has 73 kilograms of emissions associated with it. Now we understand, what the actual carbon footprint of a particular, use in our building is, and we can start to make some decisions by adding the emissions factors for those materials into our decision making. So essentially, Beam is a spreadsheet tool. What you do is input some information about your project, including in particular dimensions of your project. You can use Beam in a bunch of different ways. If you just want to, say compare some insulation materials, you can just put in an amount of area in the exterior walls section and only look at insulation. Or you can, model out an entire building or sort of anything in between. You can do just, say, wall assemblies or roof assemblies or floor assemblies. So there's a bunch of levels of use in terms of, comparing material by material or assembly by assembly or on a whole building level. But the second part is, once you put in your dimensions, those kind of get input through to the other pages on Beam. And you can sometimes you have to add some additional information. So for insulation materials, R value is another variable that you can add. And then once you do that, once we've got your dimensions and your R value, we can show you, all the different materials that you could choose to put into that building and the carbon footprint of those materials. And then in Beam, you would sort of check which one you're going to use, and it adds to a running total for your whole project. At the end of that process of going through all the materials in the building, you are kind of taken to this review sheet that summarizes all the selections that you've made in your project. It does some color coding to show you what some of your higher and lower carbon footprint materials are, and it gives you both the net emissions, a total emissions, and if you've had any carbon storing materials, it'll show that as well. So you get a sense of now the carbon footprint of your whole building. And then it gives you a bunch of data that you can share with other people on the project team or your clients, including the amount of emissions by section of the building, so by footings and slabs and foundation walls, et cetera, all the way through, so all the assemblies, and kind of gives your building a rating based on all the other buildings that we have looked at in Beam. So it gives you sort of like, are you on the average side, the high side, the low side? All of that will kind of show up in the final Beam report. And one of the things that Beam does that not all life cycle assessment tools do is we do account for carbon that is stored in building materials. Typically, that is biogenic carbon or plant-based carbon. There are also some materials starting to use mineralized carbon. So where carbon, CO2 from the atmosphere is used as a feedstock, say in concrete or another. So we start with the emissions that we get reported in the EPD. We assess the amount of carbon that's stored in that material. We knock it down by 10% just to sort of be safe. And the total emissions minus the carbon stored gives us the net emissions figure that we share in BEAM. In BEAM right now, we count carbon that is stored in residue and waste material products, and not in virgin timber products. So we're kind of trying to capture the carbon that is drawn out of the atmosphere by all of these materials growing, but that typically goes back into the atmosphere fairly quickly as waste, whether that waste is burned or landfilled or in some other way disposed of. That carbon cycle is sort of the natural way of things. And what we're looking for is materials that interrupt that process and put the carbon that was going to go back to the atmosphere in short order into a building and store it for a longer period of time. We do this because climate science, sort of tells us that taking carbon out of the atmosphere and storing it, even for relatively short periods of time, has a meaningful impact on the climate. So the ton-year methodology that's used by the IPCC and lots of climate scientists, measures both the impact on the climate of emissions releases. So in this graph, you can see, 1 ton of emissions released to the atmosphere of CO2 today stays in the atmosphere for over 100 years and sort of does what they call 46 ton years of climate damage. It sort of warms the climate over the period of time that it's resident in the atmosphere. And so over 100 years, that burst of emissions does 46 ton years of climate damage. And so on the storage side of that, if we can store a ton of carbon for 46 years, we have offset the damage that 1 ton of emissions would have made to the climate. So there's a time period there, and it just so happens that most of the materials that do store carbon in a buildings are great places to store carbon because they are relatively durable. They do last this 40 to 50 years that we need to offset those emissions. And so even when that carbon comes out at the end of the building's life, if it's been there for at least those 46 years, it has fully offset a ton of emissions. So that's kind of the way that we account for carbon storage in BEAM. And so if you use BEAM, you'll see some materials have a net positive number. So that means they're net responsible for emissions, and a few materials will have a net negative number, which means that they're providing this storage capacity that offsets emissions. So I was going to pause there and take any questions that we might have sort of on the methodology, and then I'm going to get into some of the studies we've done and things that you can do as designers and builders to reduce this. But I wanted to just pause and make sure that folks feel comfortable with that methodology bit.
Yeah, this is great, Chris. What happens when the builder wants to do a model and the environmental product declaration or EPD doesn't exist? How hard is it to convince manufacturers to do these? Can they still do a model? What can they do to talk manufacturers into doing this?
Yeah, that's great. One of the things you can do is just ask manufacturers to do this. More and more manufacturers are doing it, and in fact, the new IRA bill in the U.S. Sets aside quite a substantial amount of money for material manufacturers, particularly in the building space, to be able to access funding to do EPDs. So manufacturers that haven't done them to date, maybe because of cost, There's going to be a pool of money available soon to help encourage more EPDs. Right now with Beam, we feel that we have, all the materials that a residential builder would use are well captured there. Maybe not by the particular manufacturer, but at least at the industry scale. So there's a few different levels of EPDs. One is sort of manufacturer-specific one. So, a company does an EPD on their particular product. That's great. That's kind of the ideal, and Beam has as many of those as exist. But there are also industry average EPDs where a whole bunch of manufacturers will get together and do an EPD that kind of covers, all of their activity. And so you get basically an average of all of them. So things like lumber right now and concrete are often represented by one industry average EPD, which is great in terms of, showing us in general where that material would land. But obviously there can be really big differences between manufacturers, so you don't get that degree of resolution. But between manufacturer-specific ones and industry ones, pretty much every material that you would use in a residential project is there in Beam in some way. And the ideal will be when every single product that we want to use has its own product-specific EPD. But for now, we have enough that I can't think of very many materials that would go into a building that aren't in Beam in one of those two ways. So it's fairly well represented, but the more the manufacturers can do, not only EPD specific to their manufacturing, but if they can get it specific down to the plant, if they have more than one plant, the better we'll be able to use that information. But if there's anything you see that's missing in Beam, the thing to do would be to write to the manufacturer and say, look, I want to buy your product, but I need to know what its carbon footprint is. And so, if you can produce an EPD, I'm much more likely to buy that material.
Another question that came up was, I keep wondering about the longevity of materials in your equation, and if your rating structure is built to last for hundreds of years in your methodology in terms of materiality.
No, we're not measuring to the hundreds of years. We in Beam, we're sort of only including materials that have, typically in the range of sort of like at least a 20-year lifespan and onward, because the impact, the time impact, we don't have very much time to really make a big difference here. And the assumption that making a building, say you have double the carbon footprint in the materials, but it lasts for 200 years. The way the kind of state we're in with the climate right now, it's not necessarily justifiable to have a much bigger carbon impact today in the hopes that but that stands over the next couple hundred years. If we continue to emit and in fact drive our emissions up by using that that strategy, we're just not going to be able to know that we're going to have a climate that we can continue to live and build in 100, 200 years. So that's not to say that I don't think the longevity of the materials is important, but we're there is a window of time, and depending on how you read the climate science, that could be 10, 20, 30 years, but we're measuring it in decades that we have to make a meaningful impact here. And so reductions that we can achieve now are critical. And if we take the material carbon stuff seriously now, one of the issues with sort of speculating on the length of time and the replacement of materials is that we assume today that if, I have to replace this, say, cladding on the building in 25 years, the assumption we make is that the cladding that we replace it with will have today's carbon footprint. And, we can be pretty certain that it won't. The drive to making these materials more carbon efficient or even being carbon storing means that it's quite likely that when it comes time to replace materials, we'll be replacing them with better low carbon or carbon storing options. So it's a long-winded way of saying we're really focused on the upcoming decades where we're going to either sort of make or break the climate in terms of it being stable and hospitable. So that's where the focus is on BEAM, is on the emissions impact that you will have right now. And that's not to say that I or the organization don't think that longevity is important, but it's not a reason to make a huge carbon trade-off, I don't think.
And this last question before we transition, or maybe this question is in your next part, but I just want to put it out there if it's not. And thanks to our member, Michael, who I think is maybe an early beta user, because he identified previously you had timber in there. Timber was initially in the beta version as carbon sequestrating, but now is not. Can you elaborate? And then FSC, SFI?
Sure. Yeah, that's we could do a whole webinar on this topic, so yeah. I'll kind of try to condense it down. But essentially, there's a lot of debate about whether or not timber is carbon storing, and the reason that we've dropped it from BEAM right now as a carbon storing option is just there's way too much uncertainty as to whether the amount of carbon in, say, this 2x4 or this sheet of plywood or OSB in my building has had a meaningfully positive impact on the climate. And that's because all the other materials that we're measuring, that's why I sort of specifically called out sort of residue and waste materials. We know for certain that all of those materials were going to go back to the atmosphere as emissions very soon. Whereas with a forest, if you just leave the forest alone and don't cut down the trees, those trees aren't emissions. Those trees continue to absorb carbon. So the forests are the biggest or among the biggest carbon sinks on our planet. And so when you cut a tree down, first of all, you're cutting down something that was likely going to go on storing carbon. We tend to cut down trees early enough in their lifespan that they actually had decades more high impact carbon storage to do. So we kind of interrupt that. And then that tree that we've cut down, less than half of that wood that we chopped down is actually going to make it into your building as stored carbon. So if the other 50% of the tree goes back into the atmosphere as slash on the forest floor, as stuff that was burned, sawdust that was burned to run the kilns in the building, if half the carbon stored in that full tree goes back to the atmosphere and half of it makes it into your building, you haven't actually done anything positive for the climate. There's as much emissions in the atmosphere as in your 2x4. And so all of that means that it's really hard to say, yep, put wood in your building. We can easily calculate how many carbon atoms are in there, like what the actual weight of carbon is. But I think we just felt it wasn't certain enough. And in fact, in a lot of ways, we know for sure it's not certain that carbon stored actually helped the climate. FSC and SFI, those certifications are working on ways to try to use carbon as a metric in their life cycle assessment. So right now, we don't count really important things like what happens to the roots that were abandoned in the ground. 20 to 30% of the mass of the tree is left, in the ground. What happens to the lag time? When they replant trees, that's great that they replant them, but the mature trees were absorbing carbon at a rate that the seedlings won't match for a couple of decades. What happens to the carbon that comes out of the soil when you disturb the forest and remove those trees? That can be a really large source of emissions. So currently, we're not counting any of that stuff in those programs. So, people will kind of say, well, FSC would, we can take that as a proxy for carbon storing. But I think, anybody who I've spoken to who's knowledgeable about climate and forests says that it's not. And so, we're trying to be as realistic as we can be with BEAM, and that made us sort of like pull back on the sort of initial beta tactic of showing wood as being carbon storing.
Great. Well, thanks for elaborating on those, and we'll let you dive into the tool.
Okay, great. So what I'm actually going to dive into is some studies that we've done using the tool, because it's interesting to look at materials one by one and kind of see which materials are, which types of materials have higher and lower carbon footprints and all of that. But, in the end, what we do with these materials is build buildings. And so we've worked with quite a few groups and governments here in Canada on this, including Natural Resources Canada. We did a study of 190 of their sample buildings across the country. But what I want to show you here is the results of 3 studies that we did of as-built homes, which I think are much more informative than model homes. And so we did a study in the Toronto region where we looked at over 500 as-built homes, in Nelson, BC, where we did 34 as-built homes, and 13 as-built homes in Vancouver. And so what we found was at the high end, the amount of emissions ranged from sort of the low 300s to the mid 500 kilograms of emissions per square meter of floor area. This is really high. If you think about half a ton of emissions being associated, for those of you who aren't familiar with a square meter, it's just under 10 square feet. So, if you're thinking about half a ton of emissions per 10 square feet of building, there's no way that we're going to, be able to meet any climate targets at that kind of rate. We found a pretty consistent average through these 3 studies of between sort of 150 to 200 kilograms of emissions per square meter. Everything was, fairly tightly clustered there. We were surprised, there's some big differences in climate and energy efficiency levels and things like that between Ontario and British Columbia. And yet in particular, the results for Toronto and Vancouver are almost identical. And so that's really interesting. And we're seeing that when we do studies for particular developers and stuff, that sort of like 180 to 200 is a really consistent average for typical new North American homes. And then we found some sort of better results at the lower end of that spectrum, in Toronto at 116, in Nelson at 72, and in Vancouver at 138. So these are examples of, these weren't builders trying to make low carbon homes. This is somebody's business as usual. In the case of the Toronto study, their business as usual was 40% better than the average. And that's, if you think about it, most of the climate targets that we have for the next, decade or two are to try to get 40, 50% better. And here are builders already doing that. So their homes are in the marketplace. They're developers making hundreds of homes a year. And just by sort of the happy accident of the materials they're choosing, they're certainly not at this point intending to make a low carbon house, but they are doing 40% better than the average just by their own business as usual. And that, to me is really encouraging, because it means that there's that much, affordable, available, low-hanging fruit that there's no reason that all developers couldn't be getting into that range. In Nelson, we found, again, somebody not attempting to make a low carbon house, but just their business as usual was 50% reduced from the average in that zone. And that in Vancouver, not quite as impressive, but still great, somebody whose business as usual gets them down to 30% below the average. And so all of that, points to the fact that there are some pretty easy and available steps where we could take this whole sector of the construction industry and get it down where we need it to be to meet our targets over the next decade. And if we kind of scale these results out to the 2.5 billion square feet of low-rise residential building that happens in the US every year, that sort of high-end scenario is, if all buildings were built that way in the US, we'd be generating over 160 million tons of emissions a year, making the materials for those kind of like high carbon houses. In the average range, it's somewhere around 55 million tons a year. So this is kind of the likely scenario right now, that we're somewhere in that range. But that, there's ample evidence that we could get that, down by half or more to around 20 million tons a year in pretty short order. And now I'll kind of circle back around, because, there's the material bit and there's the operational bit. But what happens if we look in a study at putting those two things together, trying to look at that carbon use intensity that I talked about at the start? And these are results from our Nelson study, where we had both the energy models for those buildings and the beam models that we made. And what we found in Nelson was that the average was about 28.8 tons, and that the operating emissions were about 1.25. And so, if we're looking for carbon use intensity at, say, the 20-year mark, that sort of average in Nelson would be 54 tons of carbon use intensity over 20 years. And what's interesting is that on the operation side, it'll take 23 years of operating that building at that level of energy efficiency before the operating emissions are equal to the material emissions. So if we're looking to achieve some meaningful reductions in the next decade or two, that materials bit is actually more important than the operating bit. And don't take that as me saying that the operating emissions aren't important. They absolutely are. But when we're looking at needing to make big reductions in the next decade, the lion's share of the emissions that we're going to be able to affect over that next decade are here on the materials side. Now, at the high end of the results in Nelson, we had some buildings that were 40 plus tons per year in terms of their material emissions, and almost 5 tons a year in operating. That's a combination of the building being less energy efficient and using more fossil fuels in its energy mix. But you can see that building is going to have a carbon use intensity at 20 years of almost 140 tons. And again, there's no way we're going to be meeting any of our climate goals if this is what we're doing. And in this case, you can see that the less efficient or the more operating emissions a building has, the faster it is for those operating emissions to add up to what the material emissions were. So even though this building had a lot higher material emissions than the previous one I showed you, because the operating emissions are going up so quickly, it only takes 8 years of operating the building before the operations outweigh the materials. And then finally, at the more positive end of those results, we had a best result building where the whole house was only responsible for 12.9 tons of emissions in its material. And it was a relatively energy efficient home using clean, renewable electricity. And so its operating emissions are down, well under a ton, actually 0.18 tons per year. And so that means that its entire carbon use intensity after 20 years is only 16.5 tons. And if you think about it, that's less. So this building was both built and operated for 20 years on less than what a couple of the previous buildings I showed were just their material emissions alone were higher than that. So, really the win-win scenario here is where we're doing a good job on both of these. Like we need to drive the material emissions down and we need to drive the operating emissions down. And when we can do both of those things, then we start to get these really great results where, that 16.5 tons over 20 years, that building, that house is less than a ton of emissions per year in total. So that's, we're not trying to encourage only addressing materials, and we're trying not to encourage only addressing operations, but by using carbon use intensity, we're trying to stress that we need to look at both. And in this case, once you get those operating emissions down by being more efficient and by using clean energy, it's going to take 100 years before the operations equal the materials. Even though materials are quite low on this one, they're going to represent, even at that low number, the majority of emissions over the next century. Now, one of the things that we wanted to look at in Nelson was we wanted to make sure that there wasn't a direct trade-off between operational emissions and material emissions. And so in British Columbia, they have a 5-tiered energy code. And so step 1 is kind of the basic code minimum. And what was interesting in our results is that, we saw step 1 buildings at the high end of the embodied carbon side, the material emission side, and we saw step 1 buildings down at the low side, and also kind of, like they bracket the upper and lower end. And so, it doesn't appear that building at code minimum has necessarily a direct impact on embodied carbon. You can choose materials to get there that put you either at the high end or the low end. And we saw that throughout. So step 3, which is kind of obviously in the middle of their range of energy efficiency, we had step 3 buildings also at the high and the low end of embodied carbon. We had step 4 buildings at the high and the low end. And we had step 5 buildings, which, if material emissions went up by making the building more energy efficient, you'd think you'd find these all at the top of the graph. But the 2 step 5 buildings in this study landed right smack in the middle of the embodied carbon side, and both were sort of under the mean for the whole study. So, there doesn't appear to be any direct correlation between operational and embodied emissions. And this is good because, lots of times this sort of is framed as an either or scenario, like you either focus on the operations or you focus on the embodied, but there's this sort of notion that by doing really well at one, you're going to do poorly at the other, and vice versa. And what we see here is that actually you can do very well at both of them, and that's in fact what we need to be doing. We also found across all of our studies that 3 categories of materials always stood out as the top 3, and those are concrete, insulation, and cladding. Doesn't matter, whether we're looking at, downtown homes in Vancouver or suburban homes in Toronto. Those 3 held up at about the same scale across, all the studies and all the housing types. And, in fact, over 70% of the emissions from the homes come from just those 3 material categories. So that's really, as designers and builders, where we want to be focusing our attention. Clearly from these studies, windows, things like the interior surfaces category, that includes everything inside the building, the wallboard, the ceiling, and the floors. All of that together, is only around 10%. Structure like posts and beams are small, framing is small, roofing is small. It's really, insulation, concrete, and cladding that we need to be focused on trying to find the best substitutions here. And so we did that with one of the buildings in the Toronto study. So one of the buildings that was at the higher end, so it had 81 tons of emissions from the entire building, which was the equivalent of 262 kilograms of emissions per square meter. And what we looked at were some substitutions. Well, what if we used a lower carbon concrete mix? So like a Portland limestone cement with a high SEM content, that brought emissions down some. Using cellulose insulation in the walls and roof made a really big difference. Switching to wood fiberboard for the continuous insulation made a big difference. Replacing the brick cladding with an engineered wood cladding made a big difference. And for the flooring and drywall, we didn't change the material type, but we just selected the lowest carbon version of what was used in the house. So, when we look at manufacturer-specific EPDs for things like drywall, there can be quite a big difference between sort of the highest emitting drywall manufacturer and the lowest. So in this category, we just chose which manufacturers had the lowest, and that made another substantial improvement. And so just those 5 substitutions in materials made a 75% reduction in the material carbon footprint of that building. Got it down from 262 kilograms per square meter down to 66. And, if you think about multiplying that out across the sort of millions of square meters of residential buildings that get built in North America every year, that's a really substantial impact from a relatively small selection of material swaps. And I'm not saying, these are the only material swaps or, the preferred material swaps. We were just sort of looking at things that, were available in those marketplaces, were code compliant, were, relatively cost comparable. Sometimes the low carbon version was actually cheaper. Sometimes it was more expensive. But, essentially, when we look at this range of substitutions, the builder could make the house for more or less the same cost, but have, up to a 75% reduction in the house. And so that study kind of points out that there are, lots of places to intervene here. And one of the main sort of takeaways that I hope you get from this presentation and from using BEAM, if you decide to try to use BEAM to look at the carbon footprint of your materials, is that we don't have to make this incredible jump from our business as usual right now to massively, say, carbon storing house next year. If you think about the sort of the targets that we have set for us globally, quite often we're looking at sort of states and federal governments and cities targeting, anywhere from 30 to 50% reductions by 2030. Well, we have, 8 years of construction left. If you're trying to make a 40% reduction, that's only 5% a year. So if you think about some of those big jumps that were on that last graph I showed you, you don't have to make all of those jumps at once. The point I'd really like to make is that if you need to reduce by 5% a year from your business as usual, and you can do that every year for the next 8 years, you'll meet, all the targets for carbon emissions that your country, state, and city probably have. And that's not a big ask. A small change in concrete mix is all you have to do in year one, and maybe a small amount of insulation substitution in year two. If you can sort of see your way to that 5% a year, I think it's really quite manageable and becomes part of your strategy as a designer or builder. Not that you have to, jump from here to there tomorrow, but that you can sort of like plan this progression where you can find the sort of the low-hanging fruit that makes sense to you. You can find the things that are affordable. You can find the things that make sense for your clients, your subcontractors, all of that kind of stuff, and sort of make your way through these changes in a really well thought through and manageable way, because there's a huge amount of low-hanging fruit to be had, and you can kind of nibble away at it piece by piece. So that's the presentation section, and I'd be super glad to take comments and questions until the end of the time now.
Yeah, hey, great. Thanks, Chris. We do have some questions coming in. And real quick before we get to those questions, I just wanted to remind everybody that if you want to watch this session again or share it or reference something again, you can go to our YouTube channel. It should be up there. If you click subscribe, you should be able to instantly get an update when it is available, and you'll have it right there in your inbox. And real quick, for those of you watching this in the future, not right now, on demand, go ahead and head over to our Thinkific channel or GBCI channel, take your quiz with an 80% passing rate, and you will receive your CU certificate. And thanks to our good friends up in Canada, Gutenberg Certs, who have always been helping us out deliver certifications. You can get your certificate right in your inbox for attending here live today by marking certs at gutenbergcerts.com as safe and receiving your certificate there. And before we get into all those questions that are pouring in, again, we want to say a huge thanks to our board of directors, our volunteers, our executive director, Jose Reyna, and all of our top tier sponsors, Mitsubishi, Ream, April Air, everyone who helps us support our work and put these sessions on and allow us to do what we do. So, obviously, Chris, you spoke to these trade-offs, and we always talk about these trade-offs at GHI. When it comes to the 5 pillars of green, a lot of times you have to make decisions where one is, harmed and benefited. And so obviously you kind of showed us in these step 1 through 5s that potentially there really isn't a trade-off that has to be made between operational energy efficiency and reduction of embodied carbon. But what ways can people feel confident? Because, you've sort of got your energy modeling over here that you're doing, and then you got your team over here doing now your embodied carbon modeling, which is what we want, right? But maybe they're not talking to each other, just whatever. So how do we navigate that? And then when you get to answer that, or maybe this is part of the answer, is the other concerns that keep pouring in here is durability, right? Like maybe there is a trade-off between lower embodied carbon and a building that's going to fall apart and rot faster than one that wouldn't. So it's almost incorporating planning for future material longevity, operation, and embodied carbon. How do we navigate this?
Well, I don't have a magic wand to wave that's going to give the answer. Right. I think the first step is to have as good an understanding of this embodied carbon piece as you do of the other pieces. And the thing is, everybody who's watching today, if you're a building professional, you kind of already understand what the trade-offs may or may not be, right? Like it's fine to say, well, but I don't want to make a building that rots in 5 or 10 years. Well, nobody's making a building that rots in 5 or 10 years. We're smart enough to be able to, work with wood. Wood's a material that rots if it gets wet. We're all building wood frame buildings. They don't rot in the first 5 or 10 years. In fact, they can last, a couple hundred years. So we're smart builders, doing things like, say, moving to cellulose insulation. There's some building science stuff to think about for sure. But, in a lot of ways, one of the things I didn't get into here is that, obviously a lot of the materials that will lower your embodied carbon footprint are biogenic. They're sort of plant-based, wood-based, things that grow, which have the downside potentially of rotting when they get wet, but also have the upside of you can build vapor open wall systems, which are actually way more durable than wall systems that have materials that act as an unintended vapor retarder or things like that in them, or materials that don't have any capacity to store moisture when it does inevitably end up in our assemblies. So I think there's I would not want to see embodied carbon be the one and only lens that somebody uses to make their material choices. I mean, like I said at the start, I went down this path because I was looking for an additional piece of information. What's the carbon footprint that I put right next to cost, code compliance, affordability, durability, if it's a thing on the surface, appearance, aesthetics, like all of that kind of stuff, energy, performance. Those are all things that we're balancing and juggling. If one of the low carbon options strikes you as like, wow, that's not for me, like I'm not going to put, say, wood siding on the outside of a building, I would say that's fine. Like we put metal siding on a lot of our buildings. That's the highest embodied carbon, or one of them options that we can do, but I do it because it's available, affordable, dismountable, repairable, it's got all these great things. So, for that material, that part of the building, I'm not maybe going with the lowest embodied carbon, but what I'll do is say, well, if I want to clad this building in steel, I'm going to need to, use the lowest embodied carbon, maybe insulation and flooring and interior wall partitions as I can. And that's how I get to my target number. And I think you can think about the embodied carbon piece a lot like you think about your energy model. Like, if you set yourself a target, an energy efficiency target, whether it's a percentage of, what a code minimum would be, or an actual, energy use number, like a certain number of, kilowatt hours or joules of energy or something like that, then you look at your building design and you go, well, are these triple pane windows my best path to that? Or is it adding more insulation in the attic and the walls? And you weigh that up. You're like, well, the windows will cost this and the insulation will cost that. And, the result will be the same. So I invest in the insulation, not the windows, or vice versa. And I would say, the embodied carbon piece, it just goes into that same equation. It's sort of like one more thing to juggle, but it shouldn't be the one and only piece of information you use. But I think it's an important one, and it sort of adds to that juggling act that we all do in the building world of trying to do the best in terms of buildability, cost, durability, what your customer wants, all of that kind of stuff. And I think it's a lot of the places that you'll make a really big impact in your carbon footprint are things that your client are never going to notice, and that aren't necessarily big ticket items that are going to cost you more. When we did our study for the Canadian government, when we looked at the material cost and the carbon footprint of all the materials in the study we did for them, there was absolutely no direct correlation between cost and carbon footprint. So sometimes the low carbon material also had the lowest price. Sometimes the low carbon material had the highest price, or vice versa. Like it was completely random across the distribution. And so, it's not a case of, well, I can't do better in embodied carbon because I can't afford it. There are lots of cost competitive and sometimes even like cost favorable ways to pick the winners. And sometimes you will go with the higher embodied carbon material for a bunch of reasons that aren't embodied carbon. But I think just having a sense of the numbers, having a sense of where you can make those big impacts, where it's worth making some of the trade-offs and where it isn't, that's the place to start.
Speaking of cost, I'm glad you brought that up. Do you find that things typically that cost more just tend to have more embodied energy as true, or is this asking people to spend more money? Because right now, asking anyone to spend a dime more is a hard ask, much less, we're watching projects fall apart left and right that can no longer meet the goals with inflation just going up significantly. So what are your thoughts there? What are you seeing, or are you not seeing anything on the cost side?
Yeah, I mean, I think, like I said, there isn't a direct correlation between embodied carbon and cost. So for example, if you look at Beam, you can go, oh, these two drywall manufacturers whose products I think of as interchangeable and that are very cost competitive, one has a big carbon footprint and the other's much lower. So like there's a no cost switch there. Same goes with lots of insulation types and manufacturers. It's like, well, the rock wool by this company has twice the carbon footprint of the rock wool by that company, but the performance, the cost, all of those things are the same. So there are some places where you can just make those embodied carbon choices and they don't have any impact. There are some places where it's actually cheaper to do the low embodied carbon option. One of the things we talk to with developers here in the Toronto region all the time is, almost every new home here has brick on the outside. It's both the most expensive and the highest carbon footprint option.
Yeah.
That there's a place where you could make up some budget on both, switch away from brick or move to face brick, or, do something to bring that down, and you bring down both the cost and the carbon footprint. So there are some wins to be had there. Concrete is one of the big ones. And for us, it costs no more to ask for a high SCM concrete mix than it does to ask for the regular mix. There's a huge carbon footprint win for no cost there. So, there's not like I said, there's no direct correlation. Some of these things that'll make a big difference to your carbon footprint cost nothing or actually cost less. And some of them do cost more. And like, that's where you do that juggling act of, where's the best kind of, bang for the buck. And we do that on the energy efficiency side all the time. And, this is just another thing to kind of like throw into that mix of, figuring out the trade-offs, figuring out what does and doesn't cost, what's affordable, what's available, what can your crews work with, all of that kind of stuff. And I think, if you, like I said, you don't have to make huge changes. Like sometimes it might just be a brand change. That gets you your 5% reduction that you need this year, switch from brand A to brand B. If you're trying to hit 5% on top of that next year, maybe that's another brand change. The next 5% is maybe talking to your concrete, supplier and talking about lower carbon mixes. There's your 5% for year 3. Like it's not like you have to go in and whirlwind and, pull the rug out from under your own feet and do everything at once. I think, if we are looking for 5% a year, the first 5 or 6 years of that are just the sort of easiest low hanging fruit where you won't find any cost implications. And, it might only be, 8-10 years down the road that you're getting into places where you're like, oh, I'm going to have to now spend a bit of money to, to make my next 5%. But I think that's, that'll be down the path because there is so much low hanging fruit available early on.
Yeah, and when you're doing energy modeling for the trade-off of upfront costs versus continuing costs, that makes a lot of sense. Obviously, at this time, nobody's paying us to save embodied carbon. But I want to note and kind of address the celebration here in the United States of our passing of the Inflation Reduction Act. And I'm excited about our friends over at Rewire America, who's put out some really good details as far as housing on just the amount of money that's going to be available, maybe $1,400 for heat pumps and electrification and insulation, up to $5,000 for zero energy ready single family homes, and several thousands for multifamily development, and extensions of solar power and geothermal tax credits. So Rewiring has a great, I'm just putting the link in there, document for that. They even have a calculator that just came out, so you can calculate it for your house and your clients that you're working with to see what you might be eligible for. But there's a little goodie that got thrown in there. It sounds like that has to do with embodied carbon that might start generating more conversation. Chris, can you speak to that briefly?
Sure. Yeah, there's actually a great report on RMI's website on the sort of embodied carbon funding that's available in the Act. But there's a lot in there for federal agencies for their own procurement to sort of to fund federal projects for using low carbon materials, which works as a great lever for manufacturers. So the one thing it does is federal projects will only start to use materials that have an EPD, and then they will start to use options from the lower percentiles of those EPDs. And so that kind of impact on federal procurement will kind of trickle down to everybody as manufacturers kind of compete for that federal business. Like I said, there's a bunch of money for manufacturers to make EPDs in there. And there's a lot of money for research and development and sort of for materials manufacturers to work on lower carbon versions of their products now. Prior to the Act, the Hestia grants from the U.S. Department of Energy, that was quite a bit, $50 million to specifically develop carbon storing materials within the U.S. So there's lots of activity right now on that side. There's also cities and states starting to look at encouraging builders to build low carbon. The city of Vancouver is about to put its project out where builders can get a fairly significant amount of money, up to $50,000 back for doing a zero embodied carbon house. But there's a bunch of thresholds, from 30% savings to 40 to 50, et cetera. But, some actual subsidy money coming in that way. And I think we'll see that program mirrored by other cities and hopefully states in the future. So, and also there are some organizations that are starting to pay people for their for stored carbon, particularly in buildings. So Aureus Earth and Puro.Earth both have just programs that are just starting, but the idea is to pay builders for carbon that they store durably in their buildings. So I think there are some financial incentives definitely coming along the way. But I think, the developers that we've worked with here in Ontario, like, really they're telling us what you're prescribing for us doesn't cost us any more, or the few things that cost a bit more are offset by the things that cost less. But what all of them have said to us is like, yeah, for the same amount of money, we could be making a house with like 40 for 50% less upfront embodied carbon, and there are budget trade-offs, but the actual, cost of the building isn't anymore at the end of the day. So I think, a whole bunch we can do for no extra cost because it's what we should be doing. And I think there are, some financial incentives coming along to act as a bit of an additional carrot there.
Mm-hmm. Yeah, that's great. And so I just wanted to give another announcement to our friends over at the Northeast HERS Rating System Alliance has formed sort of an embodied carbon task force, and they've actually put out a letter they would like everyone to sign. Those of you who engage and use HERS index ratings, we want to ensure that ResNet is considering and adopting embodied carbon within the application. So just imagine if we could both measure energy usage and embodied carbon kind of all in one. So you can sign on to that now and help us get the word out and encourage the adoption of that. On the tool usage, Chris, just some questions here about its availability, its applicability. Is there places that it's limited on the planet anywhere to certain climate zones or countries, or is it pretty adaptable anywhere? Beam is really North American focused. So, you'll kind of find we particularly selected material types and manufacturers that are, here in North America. Mm-hmm. Or if we're using, say, some European materials, it's because those are, manufacturers where people are importing those materials. But we tried to give it a real North American focus. And in fact, for some things like concrete, you can actually look at Canadian concrete mixes, US concrete mixes. So, but we really tried to focus it on the North American market. And in terms of limitations, we're limited by the number of EPDs that are out there. So in some categories, the range of options is really complete. Insulation is a great example of that. Like, there's everything from, all the different manufacturers of all the conventional insulations to, some of the alternatives like, hemp wool bats and sheep's wool are in there too. So, those kinds of things are really well represented. But essentially our limitation is the data. The more manufacturers or organizations that do EPDs, the more we can sort of build up the beam. But what we found in doing, I think we're close to 1,000 models now for all these various studies, is that, there's rarely a place where we can't capture a reasonable number for materials that builders use. It might only be an industry average number, but if that's all that exists, then that's what exists for now. But it's typically a North American average number, so it's at least giving us a reasonable ballpark for that material. But in more and more categories now, there are sort of manufacturer specific ones coming out. So, I don't think we've really, run into something where we've looked at a model and go, oh, we have nothing in Beam that that can give us at least an approximation on that. And in general, we have pretty good manufacturer specific options for different categories. When it comes to reducing operational energy, one suggestion we give to people is just straight up build smaller, or really build right-sized, right? And build density. So, and a lot of people don't like this, especially those who build bigger homes, but it's just science, right? If a space that you have to heat, cool, and ventilate, the larger it is, the more you have to heat, cool, ventilate, and light it. It's just people get mad, but it's like, hey, this is just the science, so they want to ignore it, whatever. And that plays out in many aspects in our life. But obviously we say, okay, you want to reduce your energy usage, build right size, build more strategically, smaller, scale up multifamily housing. How does that play out with recommendations for embodied carbon? I'd imagine something smaller is going to use less energy. I see you use the energy use per square foot, which tends to offend people less, right? If we, when we use operational energy per square foot, typically it rewards larger buildings and actually punishes smaller buildings. And I see you're using those carbon per square or kilogram per square meter in sort of your study. So just, I guess, talk to me a little bit about that as being recommendations, or do we want to kind of stay away from the sizing and really focus on the material?
Yeah. I mean, the funny things happen with the sizing when you're looking at embodied carbon, in that, like, if you have the exact same suite of materials in a bigger building or a smaller building, then the embodied carbon will go down in the smaller building. Like if every material type is the same, then you'll see a reduction. However, it is possible, especially when you get into, relatively high volumes of, say, carbon storing materials, where a great big house that's stuffed to the gills with carbon storing materials will, look way better per square meter, might even get into, net carbon storage territory, versus a small home where you use all the most, the materials with the most embodied carbon. The actual number may be similar for both buildings, but per square meter, the big one will look better. That said, like, it's, I think, we've cautioned in a lot of our reports, which, if people want to read the full reports, they're at the Builders for Climate Action website. In all those reports to various levels of government, we have sort of said that, hey, there are limitations to this, embodied carbon per square meter reporting. And, we even suggest some alternatives that you could look at, embodied carbon per bedroom, so that you're thinking more about emissions per sort of occupant or resident served, or ways of combining that with square meter. So I think, it's kind of the best and quickest shorthand that we had to start talking about this, but I think there are more refined ways of doing it. Mm-hmm. But I also think that, especially what we hope most people are doing with BEAM is not necessarily looking at their building compared to all the other buildings out there, but like version 1 of their building compared to version 2, in which case, sure, per square meter is a great way to do that, because you can play with all of those things. You can play with the size of the building, you can play with the materials, and compare, like, your model A to your model B. And in that case, per square meter is a great way to kind of measure. And I think, it's not a bad shorthand across the board. We know, if you want to figure out what are the emissions of the materials for all the new homes in the US or Canada, we could kind of take an average per square meter and take the number of square meters being built and get some sense of what that looks like. So it's a useful metric that way. But I don't think it's necessarily the be all and end all metric, but it's one that people understand, and I think serves a pretty good purpose. And one of the other things, you talked about density. One of the things that we noticed in our study is that the row houses and the duplexes we studied were pretty much across the board lower per square meter than the single family homes, and that's because a lot of the really those materials, the concrete, the insulation, and the cladding, the more units you have contained in the least amount of volume, the better those look. So, definitely even that metric, even the per square meter metric, works well to kind of incentivize that additional density. And I think if we can, convince legislators to think about that, think about how many people are being served by this amount of carbon emissions. What we would hate to see happen is, you build a 10,000 square foot house for one person, packed full of great materials, and it's, by embodied carbon intensity per square meter looks great, and you build a really nice compact small home that serves 6 people, and per square meter it looks a lot worse. But I think it's kind of the best shorthand I think we have right now for ways to compare between buildings.
Sure, fair enough. So a specific question about the tool, if you want to help one of our members out who's actually using it, is just quickly, what is the difference between floor area and framed floor area? I
don't think there should be a difference between those two, but just framed floor area, about framed floor. So floor area, if you have say a basement and a first and a second floor, the framed floor is there to capture the framing and the sheathing and the flooring that you put on those floors, and say the basement floor, if it's a concrete slab, is distinct from that. So total floor area would add all of those up, but because they are made of different materials, we sort of call out framed floor area so that we can figure out, say, how many floor joists are in there and how much OSB went down on top of them to cover them.
Got it. Hopefully that was helpful, Michael.
Yeah. And just for people, just if I could throw it for people who are sort of using Beam or wanting to use Beam, we do a sort of course that you can find at Builders for Climate Action. We took a summer break, but they'll be starting back up again in September. And so, if you're having specific questions like that, we have a whole section in that course for taking people's direct questions on the tool.
Great. And he just followed up, is that then deducting for the walls?
Typically, yes. Yeah.
Okay. Great. So, I'm looking at this chart. You had shown sort of going up to like 5 to 10 years carbon storing, and I'm assuming that's sort of equivalent to, the goal of where we want to have net positive housing, right? Housing that operationally gives more energy over the course of a year than it takes.
Yeah.
So it sounds like we could potentially get to buildings, right? It sounds like there is actual opportunity to design buildings and homes that store more carbon than they say. Is that an accurate goal to try to get to?
Absolutely. Yeah. I mean, if climate science is at all right, we have to have net zero emissions by 2050. Mm-hmm. That includes our building materials. And so that means that, to meet that goal, anything that we build has to store at least as much carbon in it as was emitted in making it, or we're not at zero. So, and we've seen, quite a few examples of buildings that are already there on the embodied carbon side today. It's not like a pipe dream. We've probably got models of at least 30 buildings that are, right around that zero carbon or even in net carbon storage territory. So it's not a completely crazy thing to think that we could get there.
Well, we'd love to convene a session with some of these developers and bring them together and talk about how we can really do this. I think that would be fantastic if we could generate that conversation, or if you were going to have one and we can point people to it. I think just to hear from people who are really doing it and achieving it, just like we have, endless conversations now about net zero energy. I think that would be, really important. So that's great to hear that it's happening. I just want a quick follow up, on solar and batteries. Are these being modeled in your tool? What do you say to the people who say, these things have such high embodied carbon that they'll never offset the carbon that it's used to build them, so it's not even worth using them? Obviously, batteries don't generate energy, so that's not a fair thing. But there's other things going on with those. But are those assessed in your tool? Can they be assessed? And just overall your response to this sort of folks who say, hey, they just produce too much carbon, we'll never offset it.
Right. They're not assessed in the tool currently. We don't sort of have any HVAC materials in the tool because really the data for those doesn't exist right now. Like, I don't have a heat pump manufacturer or any other piece of equipment manufacturer that has an EPD out there. EPDs are hard for those companies to generate because their supply chains are typically highly variable. And so, if I use X amount of copper and aluminum and say stainless steel in my piece of HVAC equipment, the person who's assembling that in, China or wherever it's being made is one day buying its steel and aluminum from here and the next day buying it from there. And, so the supply chains are a lot harder to track for those kind of materials. And so we kind of see a gap in EPD data for that reason. So, that's a piece that's missing. There are some sort of general methodologies coming out now for estimating the sort of like the MEP impacts, the embodied carbon. It's always kind of generalized, and we will, be adding something like that to BEAM in the near future. But it's sort of harder to tell in terms of the PV side. There have been quite a few studies that have looked at that sort of average embodied carbon of a PV panel, and it's usually the emissions it takes to make the panel are offset by the power it's producing in anywhere from sort of like 4 to 8 years has been the average in the studies that I've looked at. Again, the variability is huge. What's the energy you're offsetting? Like if I'm putting PV panels on my house here in Ontario, Canada, where our grid is relatively clean, its positive climate impact is a lot smaller than if I'm putting PV panels on a building in a place where the grid is, say, all coal-fired, where what I'm offsetting is responsible for a lot of emissions versus, if I'm offsetting power that's pretty clean in the first place, that payback time gets longer. But I guess my general response to that question is, if you want to be adding the carbon footprint of, say, the PV panels on a house, then you should also be adding the carbon footprint of the entire energy supply line, behind the house in the first, because you can't sort of say, well, this house has PV, so it's got a carbon footprint of X, and not say, well, the grid you're hooking to has a carbon footprint of X, and this house, owns a piece of that because, it's an energy supply. And just because I happen to attach my energy supply to my building doesn't mean that, like, if I'm going to own the full carbon footprint of attaching an energy system to my building, the comparable building needs to own the carbon footprint of whatever energy supply system it's using. And we don't have good numbers for that. Like you don't sort of have a number that says, oh, the natural gas supply system in the, northeast of the United States has embodied carbon of X, but it does. Like, you don't lay all that pipe in the ground. You don't, have all of that gear without significant embodied carbon, but we're not adding that. So if we're not adding it to houses that use that, we kind of shouldn't add it to houses that use, an independent system. And in terms of how those two would compare to each other, I don't really know. Nobody's really done a great job of trying to analyze that, because it's a major, thing to try to figure out, well, what's the embodied carbon of our entire power system, in this region?
Right.
Like, what went into making that nuclear power plant? What goes into maintaining it? All of that kind of stuff. You would have to know the embodied carbon of all the copper that joins us to that system, the wires, the poles, but we know it's big. And so sort of singling out something like PV panels and saying, well, you need to own up to this embodied carbon, without saying, well, we need to own up to all the other embodied carbon, is, it kind of penalizes that one system, I think, unfairly. And I don't think we know which is better or worse, but we do know that the sort of outcome of using renewables is better than the outcome of using fossil fuels. So I think, my inclination is, if you could do all of that math, it would look favorable for, things like PV and wind, but doing that math is a bit of a wicked problem that I haven't seen done, in any kind of thorough way.
Sounds like a fun rabbit hole for some of our university students to
Yeah.
go down over the next 10 years here and get us that report. So Well, Chris, we are at the end of our time. I really appreciate your time sticking around, answering some further questions, coming back. Where can people go to learn more, find out more, access the tool, or contact you if they'd like?
Yeah, so buildersforclimateaction.org is our website. All the reports that we've done are there. All our videos are there. That's where you can find Beam and access it. We have put it out there as a free tool now, but I would love to make a little pitch for contributing if you are going to use the tool. We're a very small org. We put a lot into it, and we're putting it out in the world for free, but it really is running right now on the sort of contributions of users. So if you find that it's useful to you, throwing us a few bucks is great, helping and improving the tool. Like I said, we have some courses on Beam that you'll find listed at the website as well. So I would just encourage people to check out buildersforclimateaction.org.
All right, fantastic. Chris, buildersforclimateaction.org. Go grab the tool, make a donation, support the movement, and let's reduce our embodied energy starting today. So take care, everyone. Have a good rest of your week. Thanks for joining us.
Thanks, everyone.
Be sure to check out all of our courses available online that you can watch anytime and anywhere to pick up your CEUs. Before you go, make sure to subscribe to us on YouTube to get weekly updates and stay up to date on green building science courses, webinars, and home tours. Thanks again.